Hey there, it's Shannon Magic Myers coming at you live from beautiful San Diego. Today we'll be looking at testing a claim about a population mean with one sample, and there are multiple methods for this. Most of the time we do not know the standard deviation, so I'm just going to go straight to the more realistic situation. So here we go. When constructing confidence interval estimates for or testing claims about a population mean, we typically do not know the population standard deviation. And what was that called again? Good, sigma. Therefore, I will only be covering this more realistic situation. If you happen to know sigma, then you would just follow the same procedures using the standard normal distribution with your test statistic in terms of Z, and you'd be using sigma instead of S, which is that sample standard deviation. So the student T distribution, usually just called the T distribution, is used when you're dealing with small, loosely symmetric data sets, or if you have a large data set with an unknown population standard deviation. It's really kind of interesting because this was named after somebody who worked at Guinness Brewery, and he wasn't allowed to publish under his real name because Guinness was worried about their recipe, and so he was able to publish under the name Student. So that's how it came about its name. So it's best to create a quick histogram of your data to be sure it's somewhat symmetric if the sample size is small, typically with n less than or equal to 30. The T distribution is similar to the standard normal distribution in shape, but it has more area in its tails. So that's going to make them fatter, wider. With fatter tails with wider intervals. Also, a concept called degrees of freedom comes into play. This means that since we do not know the value of the population standard deviation, which we know is called sigma, that's why I'm making you write it so much. We estimate it with the value of the sample standard deviation. And what was that one called? Beautiful. S. But this introduces another source of variability. And we like to reduce that as much as we can, especially with small samples, because they're already typically have more variation. So the number of degrees of freedom for a collection of sample data is the number of independent data values. The number of degrees of freedom is often abbreviated as DF, unsurprisingly. So, okay, we're not going to go too much into depth on this, but here's an example. Let's say you have 10 students that have exam scores with a mean of 80, all right? So what does a mean of 80 mean? It means that the summation of these 10 test scores, call them each xi. So x1 would be test score 1, x2 test score 2, etc. Well, this whole summation we know is going to equal to good 800, right? Because if you're averaging the test scores, you would add up all these test scores and you would divide by n to get your mean. So actually, let's write it like this: x bar equals summation of xi over n, right? Which has to be 800 over 10 because we know that that mean is 80. So here we go. Let's take a look and think about this. Let's just make up some scores. Well, we can freely assign values to the first 9 scores, but the 10th score is then dependent, isn't it? Because it's going to have to be whatever score you would need in order to get up to that 800 mark for the sum. So, I don't know, let's say we had scores of 60, 70, 90, just making them up. Let's say there's another 60, that person did well, 100, 95, 85, 80, how many is that? 1, 2, 3, 4, 5, 6, 7, 8, and then 90, we'll say. Well, if we add all of these things up, then we're going to end up getting, I added this up earlier and I got 730, all right? So what does that last score have to be? Good, the last score is dependent on what those other ones are. So 800 minus 730 equals 70. So that last score has to be 70 points. So just remember that every time you use S instead of sigma, when you're dealing with an inference about a mean or more than one mean, you have to take away 1 for each time you use S. So here we have 1 sample, so we're only estimating 1 standard deviation using the sample data. If you're dealing with inferences about 2 means, then you would have to estimate sigma 1 with S1 and sigma 2 with S2. So you would have to take away 2 to get your degrees of freedom from the number of sample values. The first 9 scores can be freely selected to any values. We say there are 9 degrees of freedom. All right, so next up, let's do an example. Again, okay, so with the t-distribution, it's really kind of cool and weird. You can see a picture of it below right here. This picture basically has what the distribution looks like for 1, 2, 5, and infinitely many degrees of freedom. And what will end up happening is that if you've got a real small sample size, if you look at the kind of yellow one, then that, do you see, has more area in the tails, right? More area in the tails. But as you increase the numbers of degrees of freedom, what does it look like it approaches? Beautiful, the standard normal distribution. So here, the table for the t-distribution is, you know, a little bit difficult to use, and honestly, since we have technology available, I think our time is better spent just utilizing the calculator and understanding the distribution. Okay, so a simple random sample of size 20 is selected. The sample data is symmetric. Find the critical value, T star, corresponding to a 95% confidence level. This question is a little bit tricky because I didn't say whether it was for a test or if it was for a confidence interval. This is sort of an assumption here that it would be this confidence level, that it would be a confidence interval. So that's how we're going to look at this. So basically, we're looking here at our t-distribution. And remember, it's going to have a wider tail somewhat. And you've got this symmetry. And so your mean is going to be t equals 0, okay? And so now what we'll do is we'll go into the technology and we'll check out what would happen. But don't forget that with confidence intervals, you're going to have a bound somewhere in here. So we have like this symmetric bound, and this is going to be t of alpha over 2. And what's that going to equal to? T of, beautiful, 0.025. Good so far? And that corresponds to an area of what? So that would correspond to an area from the left of, good, 0.975. All right. Now don't worry about this other one over here, because we've already taken care of the finding the correct area because of the fact that we divided it by 2. So if we look at the region in the red, right? So the red area is equal to 0.05. Cool, cool? All right, so let's go to our technology and find out, what would our degrees of freedom be? So n is 20. The degrees of freedom, we're dealing with one sample, will be n minus 1, which is 20 minus 1, which is 19. Good. All right. And so now, and we're looking up an area of 0.975 to the left. So here we're going to go to second distribution. We'll go to our inverse t. All right, so here what we need to put in is the 0.975, comma, and we're going to put in our degrees of freedom. And look what we get. We get approximately 2.09. All right. Now, just for fun, I want to show you the difference between the t and the z. So I'll go back to second distribution, and inverse normal is what we were using, right? And 0.975 on the inverse normal, and we don't have to worry about degrees of freedom, was about 1.96, right? So do you see that the t distribution will have wider intervals? And that is because we're adjusting for the fact that we are estimating our standard deviation. Our result ended up being that t of 0.025 is equal to approximately, what was it, 2.09. And so we used this one here is the answer, inverse t 2.09. And we were comparing to the z when we were looking at this stuff here. Okay? All right. So let's continue. We already looked at the t distribution, and so let's just write in some things about it. The student t distribution is different for different sample sizes. The student t distribution has the same general symmetric shape as the standard normal distribution, but it reflects the greater variability with wider distributions that is expected of small samples. The student t distribution has a mean of t equals 0, just as the standard normal distribution has a mean of z equals 0. The standard deviation of the student t distribution varies with the sample size, but it's always going to be greater than 1, unlike the standard normal. Distribution, which has sigma equal to 1. All right, so as the sample size increases, the student t distribution gets closer to the standard normal distribution. Cool. Here's some notation, and I'm mixing it in for, both ideas, as far as, whether you are constructing a confidence interval to estimate mu, which would be the mu here, or whether you are testing, a claim about a mean, which would be here. This would be the one that's true under the null, okay? So let's put in what we've got there. Mu is just the symbol for the population mean. Mu x bar is going to be the population mean assumed true under the null. So that, of course, would be if you were testing a claim. N is the sample size. X bar is the sample mean, which is your point estimate always for these. That's the best point estimate. And remember, that's, x bar is equal to summation xi over n. And then S is the sample standard deviation. The standard error of x bar is going to be your t star, right, times S divided by the square root of n. So we're still dealing with central limit theorem stuff. And then the confidence interval for mu would be our point estimate, x bar, plus or minus the standard error for x bar. Cool? All right, so now t, this would be for a test statistic, all right, would be x bar minus mu x bar over S over the square root of n. Cool? All right, so requirements. The sample data has a roughly normal, loosely normal, however you want to look at it, distribution. Or this is really kind of an and/or n is greater than 30. Okay. So for the critical value method, you reject the null if the test statistic falls in the critical region, which we've been calling the rejection region, and that region is found by finding plus or minus t star, which is determined by the alpha level. Okay, p-value method. Reject the null if the probability of obtaining a test statistic at least as extreme is less than the alpha level. And then confidence interval method. Reject the null if the interval of likely values does not include mu x bar, which is the mean assumed to be true under the null hypothesis. Cool, cool? All right, so let's look at an example, and we'll be using the TI-84 to calculate this. Again, I'll construct and interpret the 90% confidence interval estimate for the mean height of the jockeys by hand, sort of, by getting the summary stats. And then I'll also show you how to use it, the calculator, to directly go to your confidence interval estimate. Okay. Well, Del Mar just started, so since the winter horse racing season just opened, you are interested in estimating the mean jockey height. So let's say you randomly selected 10 jockeys who are racing at Del Mar on opening day, and you looked up their heights, because they have all the stats for the jockeys. It's pretty cool. All right, so let's construct and interpret the 90% confidence interval estimate for the mean height of jockeys in races at Del Mar. Stat, and remember in the edit, you can, the edit is the default that comes up. And so we want to edit. We want to edit our lists, okay? And even though I have these values in 2 columns, it's just one list because I did that, honestly, just to save space, all right? And you know this because it doesn't say like jockey height versus jockey weight or something. All right, so the jockey heights in inches were, I think, 60, 63. All right, cool, cool. So we got our list. So let's quit out of there. Now, let's check out what our distribution looks like. It needs to be somewhat symmetric, all right? So if we go to second y equals, that takes us to stat plot. I want to turn it on, and I want to change this to something else. I want it to be a histogram. Groovy? And we're using list 1, so that all looks good. And then let's see what that looks like. Let's go to our window. You have a zoom function. In this version of the calculator, I don't think there is one. So if we go to the window, we know our values, right, start at what? I think our minimum was 59, all right? So let's take a look at, let's go up to, I don't know, I'll just start x at 0, and the maximum x we can have be 70, I guess. And then our y minimum would just be 0. And our y maximum, I guess that'll be fine. Let's see what it looks like. So as you can see, this is roughly symmetric. All right. And so we're checking our conditions here. So this is, this here is roughly symmetric, right? And so now let's identify, all the stuff we're going to need. So here we've got our n is equal to what? Beautiful, 10. We've got 10 jockeys. So our degrees of freedom will be equal to n minus 1, which is 10 minus 1, which is 9. Awesome. Okay, and now we just need to figure out what our, t-value is going to be based on, all right? So doing it this initial way, remember that we ended up using our on this problem here, on the calculator, we need the inverse t, okay? And the inverse t, you've got to enter in your area, comma, your degrees of freedom, okay? So let's come back over here and do so. All right, so the area corresponding to T alpha over 2, which equals what? We have 90% confidence interval, so 1 minus 0.9 is equal to 0.1, right? So that's alpha. And so this would be T of 0.1 over 2, which is T of, good, 0.05. Good so far? Awesome. Which is 0.95, right? So let's do it. And let's go to second distribution, inverse t. Now this time it's 0.95, and then our degrees of freedom were, beautiful, 9. And we get approximately 1.833. T of 0.05 equals approximately 1.83. Groovy? All right, and remember that the general formula was going to be, what do you think? Good. X bar plus or minus T star times the standard error of X bar. So we still need a couple things, don't we? To do so, why don't we use our one variable statistics under the calculate menu? We'll go to stat. Now we want to go to calculate, right? And we calculate the one variable stats, right? And we're calculating the one variable stats for list 1. So list 1 is here. And lo and behold, here's what we get. And you got to remember what you're supposed to use, all right? So what we're going to use is X bar and which one? SX or sigma X? Beautiful, SX. X bar, you can see, is here. All right, and then our SX that we're also interested in is, there we go. X bar was equal to 61.2, and of course that's in inches. And then S is equal to 1.5492, and that's in inches. Groovy? The standard error of X bar, so be careful, the standard error of X bar is equal to S over root N, which is going to be 1.5492 divided by root 10. And then these are all approximate, which will be 0.4890. That's still in inches. All right, so let's finish her off. So we will have, I'll do it in our regular color now. X bar was 61.2 plus or minus T star, which was 1.83, And then we need the standard error of x bar, which was 0.4899. So we'll get 61.2 plus or minus. All right, 0.8965. And we should put our units, shouldn't we? So 60.3 inches is less than mu is less than 62.1 inches. Groovy? All right, so this is our result for our confidence interval estimate. So these are the likely values for the heights of the jockeys. So here, we wanted to construct and interpret. So the mean height of jockeys at Del Mar on opening day is between 60.3 inches and 62.1 inches, and that was at the 90% level of confidence. So how would we go straight to the confidence interval on the TI-84? Stat, test, and do you see how it gives us our interval? So this is a one sample T confidence interval is that 8th selection, all right? And look, it already had our data. Isn't that awesome? And so it had all of our data and what level of confidence that we're looking at. But here, do you see that it's not the same level of confidence? So let's go down here because we did a test. It'll default to n is 0 and it'll default to the confidence level of 95. So we knew that our n was 10, right? Our confidence level was 90. Enter. So look, 60.3 and 62.1 if you round those. And that's how you do it. So this is how you would find the confidence interval using the graphing calculator. So now remember that a 90% level of confidence gives you the same T star as you would have for a two-tailed test at the 10% level or a one-tailed test at the good 5% level. So let's see what part 2 asks us to do. You believe that the mean jockey height at Del Mar is greater than the accepted mean height of 60 inches. Use your sample data to test your hypothesis at the 5% level. Oh, so it's a greater than statement, right, at the 5% level. So that means that we have a one-tailed test at 5% level. Oh, cool. That means that we can use that T value that we had for the other one. So here we go. The null would be H0, that mu x bar equals what? Good, 60 inches. You could say less than or equal. That's the most proper thing to say. But if you want to just say equal 60 inches, that's fine. Versus our alternative hypothesis, which is that mu x bar is greater than 60 inches. Cool, cool? All right, so we want to find the test statistic. So if you recall, when you do it by hand, the test statistic will be T equals what? You remember? It'll be x bar minus mu x bar over s divided by root n. And that'll give us approximately, x bar we got was 61.2, remember, minus 60, enter, and then I got to divide that by, so we get approximately 2.45. So x bar was 61.2 minus mu x bar, which was 60, over s over root n we had found to be 0.4899. Groovy? Okay, so our picture would look something like this, but this is actually what we were being asked to find for this. We can just box the stuff we've been asked to find. Okay, now use one of the three methods. So we'll make the pictures for everything. Be something like that. And this would be t equals 0. One, 2, 3, -1, -2, -3. And so from our work before, we got that t star was equal to 1.83. So that was t of 0.025, which was 1.83. And so remember, with the critical value method, that's what you use to divide your intervals. Here we go. So the critical values are going to be the 1.83. So 1.83 will be about here. All right. So that means that this area region right here in the green is going to be area equal to 0.05, which equals that probability, right? That which is equal to the probability that t is greater than 1.83. Cool, cool. And then on the other side, what are we going to have? On the other side, we will have all of this region here. Actually, I can make this bigger. There we go. Okay. All right. And so now what we do is we see, okay, where did our test statistic fall, right? So what was our test statistic? It was 2.45. So t equal to 2.45 will be somewhere around here, right? So here, this is t equals to 2.45. And so you see that that falls into the rejection region, right? So we would say, oh, okay, we're going to reject the null. And we'll do our conclusion below. Groovy? Okay. Now, remember with the p-value method, what you do is find the probability that you would get a value at least as extreme. So, as your test statistic. So, we got t equal to 2.45, right? Which is about here. And so, that becomes our boundary level. And we want to find this probability. So we want to find the probability that t is greater than 2.45, right? Well, you've got the symmetry just like you do with the z-scores, or you can just go enter it in, you know, in the deal. Remember, your degrees of freedom are going to be equal to 9. We got that from before. So let's check it out. What we're going to want is the cumulative CDF of our t, okay? So it's a greater than, so in this one, we can say, so I'm going to put 2.45 and then just a really big number. And then I'm going to put degrees of freedom of 9. And so our p-value is 0.018. Now remember our alpha level, remember that alpha is equal to 0.05. That's what we're, so since 0.0184 is less than 0.05, we reject the null. And this one, reject the null, since t equal to 2.45 falls in the critical region. Cool, cool? All right, so what's our conclusion? Let's go back and look at our likely values we found. You see our likely values fell between 60.3 and 62.1 inches. And do you see how 60 inches is not part of that interval of likely values? So that would be the reasoning for your confidence interval, right? So let's just take a look overall. We would say that at the 5% level, there is significant evidence to reject the claim that the mean job at Del Mar, actually that's on opening day is less than or equal to 60 inches. Now, if you had just put equals as your null hypothesis, then you wouldn't say the less than or equal to. All right, and we could also add in that furthermore, the 95% confidence interval estimate of the mean jockey height at Del Mar on opening day is between 60.3 inches and 62.1 inches. This does not include 60 inches. Right? So we've got evidence in all three ways to reject that null hypothesis, and I will see you soon, and we'll be looking at whether there's a difference between two means. Okay? Have a fabulous day. Bye.